Hey guys, it's Mr. Brewer here to bring you a lesson today in energy again. Today's lesson is going to focus on a type of energy called mechanical energy. And one of the things that we should probably do is boost your confidence a little bit. So I got out the old coach's hat and I'm going to coach you up a little bit. One thing that you should recall from very recent learning or very recent lessons is that there are two kinds of energy that we were worried about calculating. One called potential energy, when that energy is caused by gravity. The height, h, of an object determines how much energy is stored in that object. The other formula called kinetic energy, the mass and the velocity of the object will have a lot to do or actually determine the amount of kinetic energy stored. So what we're looking at today is something called mechanical energy, which at any moment in time, we kind of think of as the sum of these two kinds of energy called potential energy and kinetic energy. So if we take a look at the roller coaster here, what we can see is we can take a look at what's going on with kinetic energy and potential energy. If you notice, the green bar is staying the same. What they're telling us by this is they're telling us is that the total amount of energy present, called mechanical energy, is always the same because the kinetic energy is really the result of potential energy being converted into that new form. So as we watch the display here, what we're going to see is we're going to see changing amounts of kinetic energy and changing amounts of potential energy as they convert back and forth in that idea that we call transformation. So the total amount of energy is always the same. It's just what type of energy is it? So if we can just wait till the roller coaster comes back to the beginning of the slide, what we'll see is we're going to see when the roller coaster comes back to its highest point, the potential energy will be at its highest. And what will happen is it'll begin to fall, and the kinetic energy will build up as it's falling, and the potential energy will drop. So here we go. Potential energy begins to fall. Kinetic energy is building, and it falls. Kinetic energy, when it reaches the bottom, is at its highest point. Now it climbs. Kinetic energy goes down, right? Highest point, kinetic energy. Kinetic energy keeps changing. So as the height or the position of the coaster car changes, so does the motion of the car. That actually allows us to predict where the slowest speeds and where the greatest speeds would be, or velocities. If we notice, the speed is greatest when we get to the bottom of the slope. So when we get to the bottom of the ride, if we look on the right of the screen here over where speed is, we can see near the bottom is where we have our greatest speeds. Near the top, when the coaster begins, is where our speeds are the least. That's because potential energy has not yet been converted into motion, which is what we call kinetic energy. So this is a visual that kind of allows us to begin to think about the concepts that hopefully we can create as mathematical ideas today. So I need you to be confident with your abilities and your skills to work within two formulas and think about what really happens as objects fall. As objects fall, the amount of kinetic energy builds up because the object is gaining speed. The amount of potential energy falls because it is losing its height. And the total amount of energy is constant because that total amount is just the sum of the potential and the kinetic energy. If we take a look at another example of this, we see the same sort of thing happening with a pendulum here. As the pendulum swings back and forth, when the pendulum gets closest to the ground, it's at its highest kinetic energy. Here it comes, right there, high kinetic energy. So as it swings back closest to the ground, as we come back to original position, what we should notice is here it comes, closest to the ground, our highest speed too. Down here where it says velocity of bob, they're not talking about some guy. They're calling the pendulum a bob, just another word for it. So we see as the pendulum or the bob gets closest to the ground, that's where our highest speed is. We see our lowest speed. As the pendulum is highest in the air, that is our lowest speed because that's where, right at this moment, the potential energy is highest. So this changing back and forth of potential and kinetic energy, the sum of those two factors is what we call mechanical energy. Let's take a look at some context here So here we have a skier, and we're noticing throughout the ride, we got all these positions, A, B, C, D, E. Each of these positions, it's showing us that the amount of energy is constant. So the amount of mechanical energy is the sum of PE, potential energy, and KE. Let's get rid of my face here because that's a little distracting for me. So we'll get rid of that. There we go. And what we want to do is we want to look at this with a little bit more care. So let me point out that here at the beginning at point A, it says the kinetic energy is 0. Well, the skier hasn't started moving yet, so it makes sense that the motion energy, called kinetic energy, is 0. The potential energy at this point is 50,000 joules of energy. Now remember, potential energy is easily calculated with a formula. So the formula that we can use to calculate that, PE equals mgh. Well, if we know that there's 50,000 joules of energy, m is the mass of the object. They didn't give us the mass of the object in the actual diagram, but we can calculate that by knowing g is 9.8, and by knowing that it is 100 meters off the ground to begin with. That allows us to calculate the mass of the skier at the beginning to be 51 kilograms. So PE equals mgh. We now know the mass of the skier. As the skier continues to ski, the mass is always going to be the same. So no matter where we are on the slope, m is always going to be 51. Well, what's going to happen is as the skier begins to ski, let's imagine he gets to point B. A fair amount of that potential energy has now been converted to kinetic energy, but the sum still adds up to 50,000 here. So if 30,000 joules of potential energy still exists because he's still off the ground, 20,000 of those original 50,000 joules of energy are now kinetic energy. Continue downward as we get closer and closer to the bottom of the slope. The amount of potential energy again goes down because our height is even less, and our kinetic energy goes up, again, our motion, because the skier is going to be moving faster the further he or she gets down the slope. Notice there's a little jump here. So as we get to the jump, woo, what ends up happening is the height begins to change. So the skier begins to store up potential energy once again. And our potential energy goes from 15,000 back up to 30,000 because the height is now 60 meters off the ground instead of being 30. Well, that means some of our kinetic energy is being converted back to potential energy. Notice, however, there's always this 50,000 joules of energy. The total ME, or mechanical energy, remains constant. So we could use this information to make some determination. Let's suppose we wanted to know what the skier's velocity was at point C. Well, at point C, we know the total energy is still 50,000 joules. We also know that at point C, the potential energy is 15,000 and the kinetic energy is 35,000. Using this information, we can determine the total velocity, V, by using the formula for kinetic energy. We know the mass of the skier, and we know what the total kinetic energy of the skier is. So we'll just simply substitute or plug in 35,000 joules of energy at point C, 0.5 times the mass of the skier, which is 51 kilograms, times V squared. 0.5 times 0.51 becomes 26.01. So we have a new version of a formula. We could divide each side of the formula by 26.01. We end up with a new version of the formula again. V squared is equal to 1345.6. Notice this is V squared and not V. Therefore, we'll have to take the square root of each side. The square root of each side. Lo and behold, we end up with the velocity of the skier, or V. So 36.7 meters per second becomes the velocity of this skier. So if we have an idea how to deal with the two formulas and understand that kinetic energy and potential energy are always the sum that make up what we call mechanical energy, making that leap to the next point in our learning is not that large a leap, but we really need to own these two formulas. So our skier's velocity, 36.7 meters per second. Let's take a look at another example. So here we have a waterfall, and what's going to happen is as the water from the river or the stream comes up to the fall, this log is going to fall. It's going to fall downward. So we're not worried about its horizontal motion so much. We're worried about its vertical motion, the drop or the fall. So what's going to cause that is gravity. So knowing that gravity causes that, this is a mechanical energy problem. The total potential energy plus kinetic energy is going to be equal to the total mechanical energy. So what we're looking at here is the situation that at the beginning of the situation here, there is no kinetic energy in terms of vertical fall. So we're going to substitute in 0. That means all the energy stored in this log right now up here at the top of the waterfall is potential energy. Well, we can calculate the exact amount of potential energy using the formula, PE = mgh. We substitute in the values. It's 100 kilogram log, 100 for m. G, the acceleration gravity causes, is always 9.8. And height, how high off the ground the log begins from, 5. Substitute that in, 100 times 9.8 times 5. We now know there are 4,900 joules of mechanical energy stored in the log. All of that mechanical energy begins as potential energy because the log has not fallen yet. As the log falls, it will begin to build up kinetic energy. So our potential energy will be converted into that form called kinetic energy. Well, what we need to realize is that as soon as the log gets to the bottom of the waterfall, all of that potential energy has now been converted to kinetic energy. So the 4,900 joules of total energy, which was potential energy to begin with, is now going to become kinetic energy when it reaches the bottom of the waterfall. So 4,900 is still the total. It's just when it gets to the bottom of the waterfall, it's now all kinetic energy instead of potential energy. So what we can do then is we can substitute in for the formula of kinetic energy. Kinetic energy equals 0.5 mv squared. So the total amount of kinetic energy, 4,900, is equal to 0.5 times 100 v squared, right? 100 because the mass of the log is 100, v squared because velocity is part of the formula for kinetic energy. We multiply 0.5 times 100. We get a new version of a formula. We get 98 equals v squared, not v squared. We take the square root of each side. The velocity of the log when it reaches the bottom of the waterfall would be equivalent to 9.9 meters per second, because all of that energy that we began with, that 4,900 joules of energy, was converted from potential to kinetic energy. Let us take a look at a second example here. So here we have a roller coaster car, and it begins its free fall from a drop of 50 meters. The coaster performs a loop that is 30 meters off the ground. What should the velocity of the coaster at the top of the 30-meter loop be? So we want to calculate the velocity of the coaster car when it gets to the 30-meter loop. Again, we have to rely on our understanding that the total mechanical energy is stored up because of the original height off the ground. So we want to start by understanding what the total amount of mechanical energy is. Well, we're going to need to know and assume that this is all potential energy when the 850 kilogram car starts at 50 meters. So we will substitute in for potential energy, 850 kilograms, right? G, 9.8, force of gravity, height, how high off the ground, 50 meters. We end up with an initial amount of energy stored as potential energy of 416,500. So all of our mechanical energy happens to be potential energy to begin with. There is zero kinetic energy before the coaster starts. It's not moving. So since it's not moving, we say it's 0. What will happen is as the coaster begins its fall, kinetic energy will begin to build, potential energy will begin to be transformed into that kinetic energy. And what will happen is it will come to down here to the loop, and it will begin to climb in the loop. As it climbs in the loop, that potential energy begins to build up again because it's now off the ground. And what will end up happening is it's going to lose some of its velocity as it climbs. So once we know the beginning amount of mechanical energy, we can compare it to the amount of mechanical energy or the potential energy at the next situation. The next situation would be the roller coaster at 30 meters off the ground. So at 30 meters off the ground, there's going to be less potential energy because that's 30 meters is lower than 50. So we'll substitute into the formula and use the height of 30 in this case instead of 50 like we did above. This now gives us a lesser or a lower amount of potential energy. This lower amount, 249,900, becomes the new amount of potential energy. The initial sum of energy to begin with never changes, however. So that means our original 416,500 joules of energy compared to, at 30 meters, 249,900 joules of energy, that remaining amount is motion, kinetic energy. Some of that energy from the original point has been converted into motion. At this point, 30 meters off the ground, the coaster is now moving. So the difference between the original amount of energy stored and the new amount of energy stored, because we're now at a different height, becomes how much kinetic energy must be left in the coaster car. So by simple subtraction, 416,500 minus 249,900 becomes the amount of kinetic energy at this particular point in the ride, right at 30 meters. Once we understand that, we can simply plug in the formula for KE, kinetic energy, 0.5 mv squared. So if we know the amount of kinetic energy is 166,600 at this point in the ride, we substitute that in. We multiply 0.5 times 850 kilograms, how heavy the coaster car was, that's our M. Our V squared, that's what we're solving for, the height. We want to know, velocity. We want to know what the velocity, or V, is at this particular height of 30 meters. Since we know the energy amount and we know the mass, that's an easy unknown that we can solve for. So we'll combine 0.5 times 850, we get 425. We divide each side by 425. That will allow us to solve each side of the equation by taking the square root of 392, square root of V squared. We end up with 19.8 meters per second of velocity as a result of this particular example. So in order to work with this idea, we really need to own the potential energy formula, the kinetic energy formula, and we simply need to realize that the sum of the potential energy and the kinetic energy, no matter where we are in the vertical motion, is always the same amount, the sum of the two. So if we know the PE amount, we'll know the KE amount because we know the sum. If we know the KE amount, we'll know the PE amount because we know the sum. I hope you found this lesson kind of useful. You may need to watch it multiple times to kind of get the point or to get the hang of what's really being asked here. But I really feel like you have the opportunity to understand with all of the information that you have here. So really the only new idea that we've added today is that we have this stuff called mechanical energy, which is the sum of potential energy and kinetic energy. So let's wrap up for the day. Let's see if we can find my face here again. How do we do that? Oh, there we go. So one thing that we're going to do is we're we're going to give an honest faith effort in trying to practice some of this new mathematical thinking that was introduced today. So I'll leave you with this today then. So why did the scientists install a door knocker instead of a doorbell? That's because he wanted to win the Nobel Prize. This is Mr. Brewery, once again, signing off. I hope you found today's lesson somewhat useful. Feel free to shoot me any of those questions that you might have. Try to be very specific. Thank you.